Okay, we're going to get ready to do more with concavity and the second derivative. What I want to do first is just look at this picture and graph f prime and f double prime on the same coordinate axes. So what I'm going to look for are critical numbers. If I take a good look at this, I've got a critical number right here. I have a minimum. The slope of the tangent line to the curve is 0. So that means f prime, I have a point right here. Whatever x value this is, the derivative at that point is 0. So I know it's going to cross the axis right there. Now if I look at this graph, the slope of the tangent lines to the curve of f, okay, are all decreasing, meaning that they're negative. So it means all of these values would be down here below. So let's just talk about, say here at 0, the slope of this tangent line to the curve, maybe it's negative 1. So I'd have a point right here at, negative 1 or negative 2, just depending on what it is. This is going to create a straight line because this is an x squared. We know if we take the derivative of an x squared, we get a straight line or an x function. So let's look at this a little bit further. If I look at the slopes of the tangent lines to the curve on the right-hand side of this, it's all increasing. So the f prime would be positive. So maybe I'll just pick this point for talk. Maybe we can say that this slope of this curve is 2. We just really have to guess about what it is because we don't have a grid to go off of. So I would take at this point and I'd say, well, the slope of the line is 2. And so what I now have is I have the graph of f prime. And remember, what this stands for is the slope of the tangent lines to this curve. So it's at, maybe this is 2. At 2, the slope of the tangent line of f is 0. And you can see that in the picture. At, maybe this is 4. At 4, the slope of the tangent line is 2. And so you can see the slope of the tangent line is 2. So there's f prime. Now f double prime, when you take the derivative of, let's just name this for the fun of it, let's just say it's 2x. If you take the derivative of that, you get y equals 2. So you're getting a constant function. Well, what I want to say is all the slopes along this curve are the same value. I'm going to say that the slope looks like it's about 1. So what I'm going to do is I'm going to take it, I'm going to draw a line that's constant. Not very straight, so I'll retry that. I'm going to draw a line that's constant, and what it stands for is that the slope is always 1. So this would be my f double prime. So for example, I'm looking at the derivative of this graph right here. Well, at whatever point this is 1, the slope is 1. So I graph 1, 1. At whatever point this is, maybe it's 4. At 4, the slope of this line is 1, so I graph 4, 1. Okay. Hopefully that helps explain f prime and f double prime some more. You will have a lot more examples like that as time goes on. This next problem is just asking me to sketch a graph. So what I'm going to do is I'm going to take these ideas and sketch this graph. So since I'm sketching a graph, I'm going to start with a graph, and I'll just make it. And then I'm going to take each piece and talk about it. So what does this mean? F of 0 is 0. Well, that's talking about an ordered pair, 0, 0. So I know I have an ordered pair, 0, 0, and I'll graph it. This part right here, f of 2 is 0. That's telling me I have another ordered pair, 2, 0. So I'll graph that. Continuing on here, it says that the derivative, the first derivative, is less than 0. We know that that means it's decreasing when x is less than 1. So right here at 1, I know that my function is decreasing. So up till 1, I'm just going to put this little dotted line here. Up till 1, I know that it's decreasing. It's going down some way, shape, or form. It says the slope of the tangent line to the curve at 1 is 0. So that means that this is a max or a min depending on what's going on. It's a max or a min. This other part says that the derivative is increasing because it says the derivative is greater than 0. So it is now increasing over here. And then this tells me concavity. And I'm going to actually finish this on the next video. Okay, I was just getting ready before I ran out of time to talk about concavity and what is going on right here. This means concavity, second derivative always tells me about concavity. So I'm going to be able to say that this is concave up. And since there's no restrictions here on what x is, I'm going to know that's concave up everywhere. So to finish this sketch, what I have to remember is that I was decreasing. So it's decreasing, so you can kind of see my lines right here. It's decreasing till 1. Then it was increasing until from 1 on. There was we can tell that it's going to be a minimum here. And I now know it's concave up everywhere. So I know it's going to go through those 2 points. It's decreasing, then increasing, and concave up everywhere. The next example I want to talk about just talks about graphing this and identifying the point of inflection. So what I'm going to do is just go ahead and find the point of inflection without even graphing it. So that means I am going to take the first derivative of this, which gives me 1/3 x to the negative 2/3. Now, I do just want to go ahead and find the second derivative because I want to know about the point of inflection. So I'm not going to concern myself with critical numbers or anything like that. I'm going to get negative 2/9 x to the negative 5/3. And then what I look at here is, well, my second derivative actually says I have negative 2 over 9, the cube root of x to the 5th. There is no value that's going to give me 0. There's nothing on top that will make the top 0. But on the bottom, I notice that at x equals 0, f double prime of x does not exist. That would be a possible point of inflection. In order to know if it is a point of inflection, 1, you could graph it, or 2, we could check its concavity. So I want to know if this is actually a point of inflection before I say whether or not it exists at the inflection point. So if I test, say, 1 into my second derivative here, I will get negative over positive, so I know this is concave down. And then on this side, I'd have a negative 2 divided by negative 9 or whatever, so that would be a positive, so that would mean it was concave up. Now, if you were to graph this with your graphing calculator, that would be this part. You got to put in your original function. You would see that it looks like this. So you can see that it's concave up and concave down. The second derivative does not exist at 0 because of this vertical tangent line that occurs right there at x equals 0. So the answer to this question, does f double prime exist at the inflection point? The answer is no. We saw that using our algebra and our calculus knowledge as well as just looking at the graph.